Hello everyone, this is Lin Li from Zhejiang University, China. I'm one of the authors of the paper, The Devil is in the Labels, Noisy Label Correction for Robust Scene Graph Generation. I'm going to explain our work in detail, and I hope you will learn something useful. First of all, I will introduce the scene graph generation task. Given an image as input, scene graph generation aims to detect all the objects and classify their pairwise visual relationships. Unfortunately, there were three inevitable annotation characteristics in SGG datasets. First, common prone. For some triplets, the annotators tend to select less informative coarse-grained predicts instead of fine-grained ones. For example, riding and on are reasonable for man and bike, but annotated ground truth predicts is less informative on instead of more convincing riding. Second, synonym random. For some triplets, annotators usually randomly choose one predict from the several synonyms. For example, head and weight are synonyms for man or woman and shirt. Third, there were many missing annotated negative triplets and may not be background. In this paper, we try to get rid of the above issues and reformulate SGG as a noisy label learning problem. Specifically, we propose a novel model-agnostic noisy label correction strategy, dubbed as NICE. NICE consists of three components: negative noisy sample detection, NEG-NSD, positive noisy sample detection, PORS-NSD, and noisy sample correction, NSC. Firstly, in negative noisy sample detection, we reformulate it as an out-of-distribution detection problem, regarding all the positive samples as ID training data and all the unannotated negative samples as OOD test data. We utilize a confidence-based model to solve the problem. It consists of a classification branch and a confidence branch. The former predicts a probability distribution P over all positive predict categories. The latter predicts a confidence score C, which indicates the confidence of being an ID category that is foreground, when C is larger than theta. We assign predicted pseudo-label to the samples. The training loss consists of a weighted cross-entropy loss and a regularization penalty loss to prevent the network from always choosing C equals 0. Then, in positive noisy sample detection, we use a clustering-based algorithm to divide all positive samples into multiple sets and regard samples in the noisiest set as noisy positive samples. The clustering results are based on the local density of each sample. Specifically, we utilize a pre-trained SGG model to extract all visual relation triplet features H. Then, we use the Euclidean distance D to measure the similarity between two samples, and we define the local density rho of each sample as the number of samples whose similarity distance to it is closer than threshold cutoff distance DC. A sample with higher local density rho means that this sample is more similar to the samples of the same predict category. Finally, we use an unsupervised k-means algorithm with rho as input to divide all data samples into multiple subsets, and we regard all samples in the subset with the lowest rho as noisy positive samples and feed them into the following NSC model for label correction. Lastly, in noisy sample correction, we use the weighted KNN to reassign new predict labels R' to all noisy positive samples. The motivation of our NSC is that predict label of a sample should be consistent with other visually similar samples, especially for these samples with the same subject and object categories. For example, for the noisy sample going chair, we can retrieve all other samples with the same go chair, and find most of the visually similar samples are annotated as go sitting on chair. Then, we compare NICE with sorter methods. From this table, we can observe that our framework can achieve the best performance over almost all metrics and benchmarks. Finally, we visualize some unseen visual relation triplets categories mined by NEG-NSD and show some visualization of our methods. We can observe that NICE can not only help detect more missing false positive predicts, such as covering, but also more fine-grained and informative predicts, such as drawing on and covering. Thank you for your attention.